As we've mentioned a few times before, the magnitude of the value of the equilibrium constant, KEQ, tells us where the equilibrium lies in terms of a reaction, whether it's going to proceed in the forward direction and make mostly products, whether it's not going to proceed in the forward direction and there'll be mostly reactants, or whether we're going to have some of both. So we've touched on this a little bit, but here we're going to have a sort of a more official note about what the magnitude of K really means. So let's look at this example first. We've got H2 plus O2 forming water. For this reaction, the KEQ is 9.1 times 10 to the power of 80. That is a huge number. To the power of 80, that's larger than, Avogadro's number. It's massive. So what that means is that when you mix H2 and O2 together, it's going to proceed completely to make water. You're not going to have a mix of reactants and products together in a soup. You're going to make completely products. So we would say, because that number is so big, that basically this reaction isn't reversible, that it is a forward reaction, and it goes 100% to completion. It makes all products. Conversely, if we look at the reaction of nitrogen gas with oxygen to make 2NO, this reaction has got a KQ that's very, very small, so times 10 to the negative 31. This is a really, really tiny number. What that means is basically that this reaction doesn't happen. Okay, the equilibrium lies so heavily on the reactant side, you make almost none of this, and we're going to have almost completely reactants just sitting together. Okay, this is really important because nitrogen makes up 70% of our atmosphere and oxygen makes up like 23% of our atmosphere. So this is a lot of what floats around in the air. And this 2NO, what happens with that molecule is it reacts with water, and water is just like floating around in the air in droplets, and it would actually make like nitric acid, which is really dangerous, one of the most dangerous acids out there. So it's really good that we're not forming this and having spontaneous acid droplets in our air. So if this is really, really big, it goes completely in the forward direction. If KQ is really small, it basically means the reaction doesn't happen. Okay, they don't react with each other. Okay, so to summarize, there's a bit of a summary here, okay, which we can highlight. If K is very large, okay, it goes 100% to completion to the products side. So if it's large, you're going to make almost completely products. If K is around 1, okay, then you've got about the same amount of products and reactants. It's a very sort of even reaction in terms of which direction the reaction's going to go. But if K is very small, then basically it means that that reaction doesn't even happen. So you're making such insignificant amounts of your products that we pretty much say that they don't react at all. Okay, so that's a little bit about K. Now, the next piece here is about a different constant called Q. So the reaction quotient, Q, is basically, it's like finding the equilibrium expression. It's like finding K, but with initial concentrations rather than equilibrium concentrations. Okay, so we find the reaction quotient the same way. Okay, we're following the same formula in terms of KEQ was set up the same way. Q, we use the same, but okay, we use initial concentrations instead of equilibrium concentrations, which we always use when we calculate K. Okay, so this happens before the system reaches equilibrium. And when we calculate Q, we can compare that number with the K value for that reaction, and that can help us predict whether the reaction is going to proceed in a forward direction or in the reverse direction, or whether it's already at equilibrium. So here, if Q is less than K, okay, if it's smaller than K, the reaction will proceed in the forward direction or towards the right. So shift to the right. So shift to the right. If Q is larger than K, then the reaction will proceed in the reverse direction. So reverse direction, which basically means it's going to shift to form more of the reactant, so it's going to shift to the left. If Q is equal to K, then the reaction is already at equilibrium. So let's see an example of this. There's some practice questions here from the textbook and 2 practice questions on this page. I'm going to do number 1 with you just to have one example with me, and then we'll do the rest in class for practice. So question number 1 here, the KEQ for the reaction below is 0.145. Which way will the reaction proceed initially if the following amounts are put in a 1 liter flask? So 1 liter, we've got moles per 1 liter. We don't need to do any calculations of finding concentration. We can just say our moles are the concentration. Here is the reaction. So we're going to start by calculating Q. So Q, remember the way we find Q is the same way we would find KEQ. So we're putting products over reactants. Our products here are bromine gas and chlorine gas over the reactants, which is BrCl, and we add the squared for the 2 as the coefficient. So there's our formula. When we're finding Q, we use initial concentration. So here we have the amounts that we're putting in. So we've got 0.02 of both of our products. So 0.02 times 0.02 for the bromine and the chlorine, there and there, divided by 0.05 for the BrCl. When we type this all into our calculator, we're going to get out 0.16 for Q. Now the KEQ for this reaction was given to us equals 0.145. So when we compare these 2 numbers, 0.16 is greater than 0.145. So Q is greater than KEQ, which means that to reach equilibrium, okay, there's going to be a shift towards the left. Okay, so shift left back towards the products. So just like you can refer back to that first page, Q is greater than K, reaction proceeds in the reverse direction, okay, towards the left side, towards the reactants before to reach equilibrium. So we'll do number 2 together in class, and then we'll work through some of those practice questions.